electropotential energy. Whenever we have a system of charges, the system has some energy stored in it because of its configuration. It might be known as configuration energy also. When we form a system, say two charges Q1, Q2, and suppose they are positive at a distance r, then in bringing them from infinity to a closer setup of r distance, some work is needed that's stored in the form of electropotential energy. You see, if you compress one spring or even stretch the spring, in both the cases, you have to do the work. Whatever the work is done in either cases, that will be stored in the spring. When it is compressed or stretched, the energy shall be stored within it in the form of elastic potential energy. Similarly, here when you are having the system of charges, the work that was done in forming the system is stored in the form of electropotential energy. You see, when the charges are similar and you are bringing them closer, the potential energy will increase. And when the charges are opposite, quite inverse is going to happen. The formula for potential energy, electropotential energy, is going to be Q1, Q2 upon R. Now, what is the meaning of equipotential surface? When there is a conductor and you have charged it, every point on the surface of the conductor, even within the conductor, will be at the same potential. If the points are at same potential, it means the potential difference between any 2 points on the surface will be 0. We would say the surface is equipotential, but very important characteristic of equipotential surface is potential difference between any 2 points is 0. And you know, E is equal to minus delta V delta X. Obviously, E is equal to 0. So, when there is equipotential surface, along the surface there is not going to be any field. Okay, one more thing is there. Along the surface there is no field for equipotential body or the surface. At the same time, electric field can always meet the surface perpendicularly. Equipotential surfaces will never intersect each other, because that will conclude that there is two directional field at that very point, which is just impossible. If there are many charges and you want to find the potential at the given point, because of each charge you will calculate the potential at this point, and then you will sum up all the, so directly you can say sigma 1 by 4 pi epsilon naught q upon r. That is the total potential, or you can just shift this sigma over here. That means you can use the terms like this: Q1 upon R and Q2 upon R, all the terms will be added. This way it will go on proceeding. This is written in shortcut. And equipotential surface, you notice somewhere that they are closer, then it will lead to one result, that their electric field is stronger. You see, when there are two charges in the system, you have known the formula for electropotential energy. Now, big question is that this energy, you say for system the energy is Q1, Q2 by R. But question is, it belongs to Q1 or Q2? You would say both. Well, then how will this energy be shared? It will depend the freedom of their movement. Suppose you calculate this value and you find this equal to 100 joule. Means 100 joule is the electropotential energy of the system. You would say this is the energy of both the charges. If one charge is held at rest, this is bound to be at rest, and the other is allowed to move, means that is set free. So, total energy would be taken by that free charge in the form of kinetic energy. Likewise, if you release this one and hold it at rest, this will use complete energy. And if you allow both to move, they'll share their energy on the basis of conservation of momentum. So, we can say that this energy that we say energy of the system, this will be used by either or both depending on the situation of their movement, but the conservation of momentum will never fail here also. So, this is one thing. Now, if you set a charge free in electric field, the charge will always move from higher to lower potential. For remembering the physical significance of potential, you should remember how water or the liquid flows from high level to low level. Quite in the same manner, you would say that charges always flow from high potential to low potential. This is automatic process. Means when in the system charge is moving by itself, suppose this is positive and this is positive, at the same time this is free as well. Then what it will do? It will start moving by itself. It is losing its electropotential energy and that is getting converted into kinetic energy. So, what's the result? If some charge is moving by itself, it is losing its electropotential energy. And when you are doing some work in bringing the charge from lower to higher potential, that means you are working on it and its potential energy will increase. Charge moves by itself, potential energy decreases. Charge is moved from outside, potential energy will increase. Now, suppose there is a charge Q and that moves against a potential difference delta V. Then this will have to do the work Q into V or delta V. You see, for potential difference, it is not the convention of writing this delta V. With other quantities, that's very common. If you want to say time interval, difference in time, you'll have to use delta T. But for potential difference, the normal practice is only V, because this is most practical. Potential difference is the only practical quantity. So, we would always prefer V only for potential difference. The charge Q moved through potential difference V, work Q into V will be needed. If the charge automatically moves from high to low potential through potential difference V, then it will gain the kinetic energy Q into V. Since this is kinetic energy, put here equal to half mv square, and you get the relation V equal to root 2 qv upon m. Means this is a very common question. Q charge moves through a potential difference of V having the mass m. Then velocity gained by the charge would be given by the relation. One more thing, that's exactly based on conservation of energy. Suppose two charges are approaching each other. They are Q1, Q2. The charges have been, just suppose they have been projected, they have been thrown this way. Both are positive. So, they are not going to collide because of the excessive repulsive force with the decrease in distance. And ultimately, at certain distance, they are bound to stop. What has exactly happened in this process? when they are getting stopped, it simply means they are having no more kinetic energy. What does it mean? Initially, they had some kinetic energy because both were approaching each other with certain velocity. But when this total energy is converted into their potential energy, electropotential energy, obviously there is no more scope of any motion or any approach. So this would be known as distance of closest approach. When two similar charges are projected towards each other, they will stop at a certain distance known as distance of closest approach. And finally, the most interesting thing, suppose I tell you there are two charges. You'll have one term for potential energy, Q1, Q2 by R. Now, suppose there are three charges. How many terms you are going to have for potential energy? You see 1, 2, and 3. For this, we have one very simple relation given by this one. For example, here the system has three charges. Put here 3. 3 minus 1, 2 upon 2 cancel. What remains is 3. Means you are going to have three terms here in this triangular arrangement, Q1, Q3 by R, Q2, Q3 by R, and this Q1, Q2 by R. Likewise, you remember for any polygon, pentagon, quadrilateral, any number you put here, you'll find how many terms for electropotential energy you are going to have.